welcome Eric. Eric Bittner is a professor at the University of Houston, Department of Physics and Astronomy. Mm-hmm. Did I get that right?
I think we do have astronomy. Yeah.
And so we're very happy to have you here. Yeah. So then let's begin with the interview. So now you've been a professor of chemistry since 1997.
That's right.
But you crossed the border to
yes, I did.
the nearby building, no?
That's
to
right.
Physics. So now you are in chemistry and physics, so formerly in the physics department, correct? And so at this moment of your career, and then you teach in a physics department. So what do you think this interdisciplinarity means to you, and why have you done this transition, and how do you project it into the future?
It actually was surprisingly natural for me to do this.
How so?
Okay, so my undergraduate degree from Valparaiso, as you mentioned, not Valparaiso, Chile, but Valparaiso, Indiana, was in chemistry, physics, and mathematics. So I have a very strong interdisciplinary starting point. And then, my graduate work at University of Chicago was very, very physicsy, and in that sense. And really, so the last year that I've been in the physics department, I basically teach general physics, which is lots of fun. And this last term I taught modern physics, which I would say is more or less what I taught in physical chemistry, except that we now teach special relativity,
right?
Which is the new, which is fun to re-go back and learn all this fun stuff about special relativity and sort of new, sort of seeing molecular physics and seeing solid-state physics and condensed matter physics at a slightly different viewpoint than we're used to looking at in physical chemistry, which is very molecular oriented, and physics tends to be a lot more broad sweeping in that sense. Yeah.
That's very interesting. So it is indeed natural.
It was a very natural transition for me. The students that I get in physics are far more adventuresome in terms of being able to go from loosely defined theoretical concepts that I might throw out at a group meeting and then turning it into something interesting. Whereas what I found with the chemistry students, you really needed to lock them down to say, okay, well, this applies to anthracene, or this applies to this reaction. Oh yeah, I can understand that reaction. The physics students are far less interested in the specific details, but are far more interested in the overall broader picture.
So the universality of physics and the level of detail and specificity of chemistry is something that you will agree
so that actually makes a nice intersection, because you're right, the universality of physics, which is trying to get this whole thing, but then we can lock it in to this one thing over here that might be new and different and gives a different perspective onto chemical dynamics.
And with your background, you can jump from the overall universal view to the microscopics of the specific reaction with much ease, and maybe you're training your students to do similar.
I think I sort of found a niche in doing that. Yeah.
Sounds exciting.
It's sort of fun, and it's sort of, I mean, you've known me for a long time, and I've got broad interest in lots of different kind of things.
Yes.
And bring different.
Like boat building.
Like boat building, yeah.
Yes.
For example, this is like, my thing. I learn a little bit about something, I know a little bit about this, and then I want to put it together. And so during the pandemic, you mentioned boat building, and during the pandemic, I built a sailboat. It started off literally.
With your own hands?
It was my own hands.
Yes.
It literally started off as a pile of plywood in my backyard. It's sort of like this idea of like, how do all the pieces fit together, and how do I start out with something that's very nebulous and put it together to something that's new and unique. And
exactly.
Yeah, it's sort of cool.
Yes, like science, no?
It's fun. It's like science. Science is exactly like this, because we all bring different skills, perspectives, personality,
pieces of this,
pieces of this, pieces of that. I tell my students, look, you're taking this class on general relativity. Okay, your research has nothing to do with general relativity, but in 10 years from now, you might find, in 20 years, you might find, there's this problem. oh, I remember solving that problem, not quite in the same context, but in this new context, I can use it.
Yeah.
And it's a toolkit.
That's how it goes.
That's exactly right.
Yes. And so sailing is much affected by climate. No? We've been very impressed with your involvement in climate science and advocacy and maybe policies.
Yeah.
So not maybe direct, but certainly interests that you might have in climate science. So is that right?
Yeah. One of the things that I did a number of years ago was do a fairly major sailing trip on the North Atlantic, and we discovered in the stomach of fish that we would catch. We just eat them, and you'd find like bits and pieces of plastic. This is out of the middle of nowhere, 1,000 miles from shore. Yeah. Well, not quite 1,000, but you get the idea.
Yes.
Middle of really the ocean wilderness, this polluted with just chunks of plastic. Yeah. And these are, now we're finding out that microplastic pollution is in every single one of us. It's
with unknown consequences.
With unknown consequences. Yes. Exactly right. Mm-hmm. And they're finding it in tumor cells, they're finding it, and who knows what the long-term consequences of society are going to be because of the fact that we have everything we touch, every bit of clothing we have, everything in our environment ultimately is derived from some sort of petrochemical process.
And do you think physics or chemistry, probably the petrochemical processes can be done differently or maybe not even done?
Right.
But do you think physics can also help in mitigating climate change?
I think so, because physics focuses a lot on like metrology and measuring and detecting and even coming up with new materials, new techniques for mitigating, or maybe even, maybe we can come up with better materials that move us away from the current materials we're using. Maybe coming up with better techniques, more efficient techniques for transportation, for light harvesting, for energy conversion, and so on, that can help us and maybe help mitigate some of this. It was encouraging a couple years ago to find out that recently that this great garbage swirl that's in the South Ocean, in the Pacific Ocean, is being mitigated, and also in the North Atlantic is being mitigated. And so there's a solution. It's an engineering solution. It's a physics solution to collect this. But are we? Is there a long-term biophysical, biochemical ramifications of all of this? Unfortunately, we're the guinea pigs. Yeah. Unfortunately.
Yes, agreed. Yeah. So now let's switch gears a little bit into your own research.
Okay.
And so if you were able to explain in any type of detail what are you currently focusing on, and why do you think it's important and even relevant?
So my entire 30 some odd years as a theorist have really been in quantum dynamics. It's not only just from thinking about the foundations of quantum mechanics, but its practical application of calculating things and understanding spectroscopy, which is how we detect what's going on in materials, how chemical reactions occur, and even now looking at how we can possibly optimize and control the interaction between a quantum mechanical system and its environment to maybe enhance the quantum properties of the dynamics of a quantum system. One of the problems that has to be overcome for large-scale implementation of quantum computing is overcoming what's called decoherence.
And what is decoherence?
Decoherence, good question. That is the thing that kills quantum mechanics. It's so if you think of quantum mechanics, you've got one part of the equation that creates wiggles. That's our coherence. And you've got another part called the environment that kills the wiggles. And that's decoherence and relaxation. But what you want to be able to do quantum computing, which is this thing that has the power to solve problems that are difficult to solve with normal computers in a faster, more efficient way, harnessing some of these coherences that are in a quantum system, those all go away if you have a thermal environment. And the limitations of a quantum computer are that you have to have them at 4 degrees Kelvin or something cold. You have to have this gigantic machinery around it to keep it cold. Because there's a gigantic energy cost in just being able to do basic quantum computing. And it's all due to trying to isolate it from the 300 degrees Kelvin.
Prevent decoherence.
Yeah, to prevent decoherence. Yeah. And if we can figure out ways to say, hey, maybe if we jiggle the environment in some different way, mechanically, optically, acoustically, however we want to do this, maybe we can trick the quantum system into thinking it's in a cooler environment than it really is.
Yeah, that's a great way to
Yeah, it's
saying
sort of a
it.
great way to. I think it's a good way to think about it.
And so now regarding research careers, in particular the way you must commit to a research direction.
Yeah, right.
I'm sure you have one way of doing it now after 30 years?
30 years, yeah. I did my PhD 30 years ago.
It'd be interesting to compare, given your perspective, how this choice is made now as compared to a choice that you would make if you were to start now your career, okay? So how would you do it differently from what it is now today?
Yeah, that's an interesting question. I don't know if I have an answer for that because I've seen how new scientists are starting off. They're far more savvy about writing proposals and even packaging their work than I ever was. And even experienced people, like if you talk to, that are about the same age as me now, I look back at my proposals from 30 years ago, and I'm not so sure they would be competitive in the same pool of proposals that people are proposing that are doing now. Not necessarily that there's like a difference in the science, but just in the difference in the way the quality and the packaging and the thought and the details and just the sort of massaging of the message that's in a proposal are now done. I think that
maybe that's beyond these details on the craftsmanship of getting the idea proposed. In general, how to choose or think of what direction to commit to. I mean, even the step before, the step where you say,
step right before that.
The step before that.
So I guess I feel that I fell into what I'm doing. Simply because I really enjoyed my PhD mentor.
Okay.
And so my son is doing his PhD right now in physical chemistry. And I told him the same thing. He was thinking, I want to work with this person because he's doing all these science articles and nature articles and whatever. And I said, do you find out about his group? Find out the personality of the person. Is this somebody you want to spend 6 hours a day talking to, working with, whatever. And if it's not, you need to be in a different group. And
maybe the same topic.
Maybe the same topic, but just a different personality of the PI. I went to University of Chicago.
There's the work environment aspect that's not to be neglected.
The work environment is really, really important. You have to have fun in the research, and if you don't have fun in your research, you're doing the wrong thing. You're not in the right group. This is what I tell my own students. If you feel that our interactions aren't productive, getting you, and if you're not enjoying what you're working on, you're in the wrong group. You need to be in a different group. And so I try to have this like nurturing. I take my students to conferences. We do fun stuff. If I have money, I'll take them to Telluride and have a group meeting in Telluride and all that. Because I think it's important to have this low barrier between the students and your PhD advisor. And when I worked with John Light, John's door was open all the time. He had this dog that was in his office that everybody would come by and pet the dog, and John would see you walk by and go in and chit chat and talk about your project or something
And that's
else.
that's how the next idea comes to you.
That's how the next idea comes from. Just sort of like, and I have a tendency with my students, and I tell them, look, when you have a conversation with me, go to your office and write down what we just talked about, because I might forget what we just talked about, and it might be a good idea. But I'll just throw out ideas, and some ideas will stick to the wall, and some ideas you might catch, and if you can catch a good one, then go work on that, and then come tell me about it.
Yes. Yeah.
But, you know,
like
some ideas are not going to work, and I might not always have good ideas.
Right. Yeah. That's completely natural. Like,
yeah, and you know, and you know, I've had this long-time collaboration with Silva, Carlos Silva at University of Montreal, and we have a unique way that we can both tell each other, come up with the craziest ideas, and be able to have the intellectual maturity to say, no, that's a dumb idea.
That won't work.
That won't work, and here's why. Oh, okay, thanks for telling me that. What about this? Oh, yeah, that's a great idea. That might not work, but this might work. And just sort of throwing out ideas without, oh, you're a stupid idiot. Don't ever work. Don't ever talk to me again. I mean, I think that's how collaborations are supposed to work.
Excellent.
Yeah.
Now, you've been very successful at understanding energy transfer molecules, molecular system, I would say. And you work a lot on this topic. And so what do you say are the best or the most important discoveries in this topic in the past 10 years or so, in energy transfer molecules? So what do you think, what would you say are key points, milestones that you will highlight?
In what kind of molecules?
Energy transfer.
Oh, energy transfer systems.
Yes.
Oh, wow. Yeah. You know, it's you can sort of see that I'm maybe getting a little bit bored with the topic because I'm sort of not working on that so much.
What's the one that excites you more?
You know, here's what I think this is what we're working on. This is what Carlos and I are working on. This is what I think is interesting. So we understand energy level. We understand spectroscopy. We understand first order effects. We understand Fermi's golden rule. Bang. Marcus told us Fermi's golden rule, and that's basically where things have set for years and years and years. That's our basis for understanding. What we're finding is that, especially when you look in two-dimensional spectroscopy, time-resolved, multi-pulse, nonlinear spectroscopy, that you're hitting this molecule with white light, and you're creating not just one particular excitation, you're creating a whole bunch of excitations in this system. Now, in most of chemical physics, we've just simply look at, here's this molecule, it's been excited, it's doing its thing. But what we're finding, especially when you put in like cavity QED effects, these molecules are talking to each other. The fact that there's a commonality between, there's a background energy transfer, background scattering, background excitation density that's interacting with your spectroscopic signal, and you can detect that. If you can detect that, and you can detect that, and the way we've shown how you can detect that is by looking at how the phasing of the spectral signals evolve in time. And that's a really, really subtle effect, but we've dug into this and discovered, okay, well, not only can this affect the phasing, but you can understand things like, are the excitations attracted to each other? Are they repulsed by each other? What is the time scale for background relaxation? How do these things play in? Whether or not this has anything to do with anything practical in terms of light harvesting, I don't know.
And these effects are not well understood at the moment, is that?
Yes, not understood. Yeah. It's just, and I think that, for example, in the cavity polariton work that you've been very involved with, it gives us a handle to sort of amplify that effect in a consistent, controllable way, and maybe unravel some of these background things.
That's a very interesting perspective, I think.
Yeah.
And talking about perspectives, and maybe as a final question, the topic of the meeting this week is molecular quantum technology, which is it could mean a lot of things or not much. but then, what do you expect of, or maybe what's your vision for molecular quantum technologies in 10 years' time or so?
Yeah, right. So, when I was in graduate school, or 30 years ago, I never would anticipate having basically the information of the world at my fingertips and have two devices that are sitting over on that couch and in everybody's pocket that gives us that information. And that's amazing. Before that, I was a big Star Trek fan.
Right.
We all had these tricorders. I mean, I have a tricorder. That iPad over there is basically the modern tricorder.
Right.
Who knows what it's going to turn into?
Right.
It's going to become more compact, and it's going to do all sorts of cool stuff. It's going to cost energy. It's going to cost money. It's going to cost all this kind of stuff. It has artificial intelligence. It can do things that are almost like magic. And so I can only imagine that things that we're thinking about today might turn into compactification, maybe better, more efficient, different ways to explore and connect to the information biome of the whole world. I mean, this is one of the, for good or for bad, the fact that one person can send out an email or a Twitter or whatever and have it reach 25 million people or 200 million people like that is, it is changing the world. It has changed the world, for better or for worse, depending on your perspective, I guess.
Yes. And you think that molecular science could enable like better implementations of the same things or same technologies?
I think so. I think that if you
or different one, or different, qualitatively different ideas.
I don't think qualitatively different, but maybe give us a better understanding of how information works and how information can be distributed and information can be shared. Because one of the things that we deal with in quantum mechanics is a different kind of information. Quantum information is different than the kind of information that we're used to dealing with. Yeah. And this is a powerful tool, technique, philosophy, if you want, for how information is distributed, can be communicated, and stored. And I think that is transformative in and of itself.
Yeah.
So even though I'm 100% sure nothing I will come up with in my theory will ever lead to some great groundbreaking technology.
Hard to tell, no?
It's hard to say. Yeah. So we've talked
that's
about
already means something, no?
It could be. Okay. For example, like when I write my National Science Foundation proposal, I have to write something about the broader impacts of my work. Now, if I was Albert Einstein in 1911 writing a NSF proposal about general relativity, my broader impact would be, we predict that this star is going to have its position apparently shifted by the gravitational potential. There's no broader impact of this. I mean, but 50 years after that, 1951, 1960s, we were putting satellites into orbit. We were talking about putting people into space, and you needed to know general relativity to find out where they're going.
You get the number wrong.
Every single iPhone device that we have uses the equations of general relativity to find out, where the next Starbucks is over there, right? Down to a meter accuracy or 3 meter accuracy.
That's very insightful. Yes, you're absolutely right.
There's no way Einstein would have known that I'm going to have this thing in my pocket that gives me that. Or why this would be important to me.
That's the actual impact of science.
That's the completely indirect impact of science. On the other hand, science should be directed toward technological problems of its day. My other thing that, I was talking about sailing. One of the big technological problems of...
That's the fire station.
Yes, it's the fire station.
It's the fire station of the city.
Okay, of the big technological problem of the early 18th century was finding out where you were, pre-GPS.
Yes.
And so people developed mathematics, calculus, Newton's equations of motion, Huygens, clocks, to solve the problem of that day. So
So we need quantum.
We need quantum mechanics. So who knows what problem quantum mechanics is going to solve today?
Excellent.
So,
that's very interesting. Well, thank you very much for your time. It was
Thanks for
very
inviting
exciting.
me. This is
quite interesting.
Awesome place.
A lot of fun. Yeah.
Yeah.
Good.
Thanks, all right.